Okay, now back to our problem. So, okay, as I said, this is the same data set coming from Kaggle. Reading the data, this is the data. Good case, excellent value, sentiment 1, which means it's positive. And now we are adding another column label, and then we are just concatenating underline label underline to this sentiment. This is just to comply with the format that fastText works. Essentially, we will do this and do some normalization and then save pandas data frame to file, because fastText directly reads training data and validation data sets from file directly. This Python package looks to be just a wrapper around the original command line application. So still a lot of things are in the raw format. So and I have this normalization function that I'll apply. It will lowercase the text first, and then it will remove the white spaces from the text, and at the end it will trim any white spaces from the left and right of that text. So this is a normalized text. The only thing that is visible is that it's now lowercase compared to the original text here. Then I'm dropping the other columns, so original sentence and sentiment are now dropped. One other thing I do is I split this whole data into train and test, and I use the same ratio, and random state is 4 as before. The one that you guys saw in bag of words is this. If you look at, let's say, the test data, the head, the first two, it should be exactly the same as the bag of words. Let me quickly show you, because we are using the same random state. Text, the atmosphere is modern and hip, cute, quaint, simple, honest. Let's see. The atmosphere is modern and hip, cute, quaint, simple, honest. So let's move on. I'm saving all the data here, then the training data, the training split, and then the test split. This is stolen from the fastText GitHub repo. It's just a cleaner way to show to printing the results of the fastText. You'll see that in a minute. So I'll define the path to train data and test data. Just one quick thing. So there is this function in fastText. From fastText, I'm importing TrainSupervise. In there, I'm using that function, and these are the arguments. Some of the arguments that this function takes. One argument is pre-trained vectors. If this is present, then when training the model, it will use, instead of using random numbers for initializing the weight vectors or weight matrices, it will use these values. It's kind of transfer learning. So it will use those and start from those values and train a model. But if not, if it's not present, it will start from some random values as usual. Normally for bigger problems, transfer learning, I shouldn't say normally, sometimes for bigger problems, transfer learning, in the sense that you start from some pre-trained vectors, result in faster and better trained models. So feel free to always check what is behind. So question mark, the name of this function will tell you all these. And at the same time, remember I show you on fastText webpage. There you can see the definition of these. So for instance, this is the path to the input, to the file that you want to train on. Learning rate is one of the knobs. If you make it smaller, I mean, essentially the higher it is, normally results in more powerful. Generally speaking, you should be careful about this. it would be more powerful model. So it might, so if you see that your model is overfitting, lower this value. Or dimension is the same. If you see overfitting, lower this dimension. Normally between 100 to 300 on like normal size problems. In our case, way lower. We can go way down, around 10, 20 dimension is fine with us. Even 100 would overfit. Window size, epoch is the number of times the whole data set is scanned for training. So the higher results in higher overfitting probability. So be careful about that. This is the minimum number of characters, and this is the maximum number of character engrams. So essentially it means that start with 2 character engrams and go up to 3 character engrams. In our model, we are gonna find embedding for those character engrams, as well as word engrams. We are gonna have 2 word engrams. This is the negative sampling ratio. So we are not, so the loss function we're using is softmax. So if there are multiple other ones, if we use negative sampling and S, then this makes sense. So for those of you that know negative sampling, it's remember, it's a technique to make the model faster, to make the training faster. It's a kind of heuristic technique for skipping a lot of updates in our neural network. So loss function softmax is one of them. Hierarchical softmax is another one. This one is having a little bit of trade-off between speed and less accuracy, but higher speed, way higher speed. Negative sampling, again, this is optimized to make things faster. And essentially in our case, we will see that this is gonna result in multi-label classification. And there is another one versus all. Based on the documents of fastText, this is supposed to result in multi-label classification. Multi-label in the sense that the labels at the end, the probabilities do not necessarily add up to 1. They might go above 1 or they might be less than 1. But essentially, we noticed that the only one that is multi-label is negative sampling. The rest are multi-class classifications. The rest will result in multi-class classification. While we are on the subject, if you also go over the documents, you will see that the training data for fastText is presented in a multi-label classification fashion, in the sense that each row could have multiple labels, like label 0, label 5, label 7 at the same time. And then behind the scene, when fastText is trained, randomly at each epoch, randomly selects one of those labels and updates that one in that round. So to let you know that the input looks like multi-label classification, but in general the output is a multi-class classification, unless you use negative sampling, or maybe based on the documents, which I have filed an issue on GitHub with them. Still haven't heard anything back. So, but in general, in our example, we will try all of these. Although our problem is formulated as a binary classification problem, we are gonna also try NS, negative sampling, which will result in multi-label classification. As long as we get good accuracy, we are fine. Our metrics are good, we are fine. It doesn't matter which loss function we're going to use. So remember, in bag of words, the space dimension was dependent on the number of tokens that you had. So this bucket size is essentially limiting the number of tokens that are considered when training that bottleneck network for finding the embeddings. All right, let's train this. If we train this on our train data, and then we are printing the results using that print results function that I mentioned. So sentiment model is going to be our model. Train model, we will test it on train data, and also we'll test it on this test data. Again, we are just passing the path to those files, and then we print the results. So you see that the number of records in train is printed, and also for test. And this is precision at 1, recall at 1. Precision at k essentially is the percentage of the top k labels that are correct. Let me actually show you one thing, because you guys, when you do, let's say this test, if I do double tap, I'll see other arguments that I could put here. So I could set k equal to 2. Oh, looks like my keyboard is not working. All right, so if I set k equals to 2, now, okay, let me do this. This format is consistent with the CLI format you guys see there. Okay, interesting. I guess since our training data only has one label per record, we can't get results for 2, but let me show you in here. This is a similar thing, but using, so you see here, like, this is the command for the CLI, but it's essentially the same thing. This is looking at the precision at 5 versus recall at 5. These are the values, and the reason is that your labels here are not just one label per document. It could be multiple labels. Let's say this: why not put knives in the dishwasher? In the training set, these are all the 3 labels that are associated with this. And that's why it makes sense that when you make predictions, you might get like in this case, when they did a prediction, they got 5 labels. You could also check here for precision and recall definitions. Anyways, in our case, precision at 1 and recall at 1 is essentially the same thing, that the same precision and recall we had in a bag of words, and we are going to go with those values. As you can guess, probably measuring the performance of fastText models is one of the weaknesses of fastText package as of now. Hopefully later they'll add more to it. But anyway, let's move on. This didn't work as expected. So this is redundant. But if your model had more labels per record, you could have it. All right. So that model that we trained, the prediction is easy. So just call the predict and pass the text, and k equals 2 we are telling, hey, give me the top 2 labels that are predicted for these documents. And these are the values. So essentially saying, you are not a cool guy, but I really like you. It is like 53% label 1, which is positive, and 46% label 0, which is negative. So as you see, these two add to 1, and essentially this is a multi-class classification, or binary classification, in other words. The same here. One other thing I should mention before getting into tuning parameters is that sometimes you want to ship this model to edge, like cell phone devices, and you care about the size of your model, so you could quantize it. And these are the parameters I found useful based on the document on fastText website. It will shrink the size of your model dramatically, so it will make it like maybe 500 megabytes of model into like 10 megabytes. It's pretty good, but it comes with a cost. It might downgrade the quality of your model. But as you see here, once I did the quantize, I could just save it, and I can still measure the quality of my model. I can make predictions, but now the predictions are different. Like if you check the predictions that I have for this text here are now different compared to here. It's not a very consistent thing. I have defined a function to extract the positive probability, just the probability corresponding to label 1 from the prediction of the model. Then later I am adding that some columns called probability and prediction and original label to my pandas data frame. This is one of them. I have added these 3 columns at the end. I do the same thing for the train data, so the train data frame has the same columns at the end. I am changing the type of train data, original label, and prediction to make them the same, either both and or on the test that I'm making both categories. Essentially, they need to be the same to run the metrics on it. we will see in a second. So the same data frames, and remember we had this metric class from scikit-learn, so we are gonna call recall or accuracy, whatever you want on this data. Again, we get these numbers similar to bag of words. So this part is kind of to show you you're not limited to what fastText provides you. So you could technically just add these columns and now run any metrics you want. So you are kind of free to have any other metrics now. But in our example, I'm going to stick to the metric that the precision at 1, essentially not even the recall at 1, just the precision at 1 that is provided by fastText. This is grid search function similar to what we had in bag of words, that 1 week thing that we had. This is another one, and quite frankly I spent just maybe one day on, not one day, few hours on this. At least 1 week is needed, but you get the idea. So I again get some parameters as the input and loop over them and train model and try to find the best. Loss function is fixed to softmax, but in fact I did behind the scene, I did try some other loss functions, actually all of them I should say. And maybe the best way is to just add the loss function here and then loop over that as well. Then you could see that I have done some iterations, and triple star is the way I notify myself, hey, this might be a good solution. And then at the end I got these parameters, so it will give me precision 83 for text, actually for train 79.79 for test, and these are those parameters. So as you see them, it will have length 3 character engrams, length 4, length 5, and length 6 character engrams. I will have word engrams of length n. So I put the parameters here, and now I train it on all data, and I save the model, sentiment model all. And if you look at the precision and recall on all data, it's again similar to that what we had. Some words on embedding vectors. One thing is that you could once you save your model, you could always load your model back to, so this is essentially saying your model is portable now. You could go to an EC2 machine or some Google Cloud machine, just send this file to that machine, and in there you will have another Python program that loads the model and starts making predictions. You could get word vectors. These are the embeddings. So remember we had size 20, I guess. Yeah, dimension was 20. So our embedding vectors have size 20. So this is the word vector that represents cute, or the word vector that represents this sentence is here. Feel free to navigate and find more about these. So let me actually show you. Like you could, if you put dot and double tab, you will see again what are the functions that are available for you. One other thing is subwords. So high quality has subwords based on the minimum and maximum character engrams that we defined. So this is the string that is the character that is attached to the beginning of the string, and there's another character at the end of the string that is attached. And then so this is a 3-char engram, 4-char, 5 character, 6 character, again 3, 4, 5, 6, 3, 4, and it's it's moving from the beginning to the end, and it's ranging from 3 to 6 character engram. And at the end we will have the word vector for this whole thing. You might have some questions like, how is this computed? These are some of the things that are not quite clear in the documentations and papers of fastText, but based on my understanding, all of these are computed, all the word vectors, all the embedding vectors are computed, and then an embedding is computed for high quality, and then they will take the average. You could also look at the words of your model. So sentiment model all, you could just print out all of the words. But in here, I'm just looking at the first 10 words. This is the end of line word. This is de and a. So as you see, I'm not removing the stop words here. Actually, all of these seem to be stop words. And these are the embedding vectors that we computed. All right, again, we can quantize the model to make it smaller and then save it. That model that we trained on all data, now that we quantize it, we see that the precision and recall is higher, is 90% versus here it was 78%. I think my theory is that since I am retraining, I'm setting retraining to true, again, since it's retraining, it will increase the precision and recall. But essentially, we know that this is kind of making it overfit because our data is small. Train unsupervised. I put it here for your reference, but feel free to check it. So in fastText TrainSupervised, there are two phases here. One is computing the word embeddings in a similar fashion to Word2Vec or other approaches, except that it also includes character engrams. And then after it finds the word embeddings, it will train a simple classification model to do the classification. But you could just stick to the first part, that is finding word embeddings. And this is what's happening here. In here, train unsupervised, it's only finding the word vectors. And in here, you could pass this model and say whether you want skipgram or SIBO, continuous bag of words. Whereas in here, I don't remember if there is this option to tell fastText which one you want to use, but I believe by default, if I'm not wrong, by default it's skipgram. I'm not sure. All right. Once you do that, also you could check the documents. Let me get to pre-trained vectors. So fastText already provides these pre-trained vectors. Feel free to check these links. And I have downloaded the Wikinews one. It has 1 million words in it, and the vectors are having 300 dimension. And now I'm training up my model similar to before, but I'll pass. So here I'm not passing anything, just the regular parameters. 0.95 learning rate, dimension 300, and so on. Bucket size 1000. This is what I'm getting. Precision at 1 is 80, 0.80, and for test set it's 0.73. Now if I pass pre-trained vectors, the same argument, nothing changes. The same argument, you see that precision at 1 is 1, and precision at 1 for the test set would be 80.81. You see the jump? This is the power of transfer learning. So you already have these pre-computed vectors, and you start from those, and then you quickly overfit. Overfitting means that your model was so powerful. And I'm gonna now suppress the power of this guy. So essentially what I'm doing is that I'm decreasing the learning rate dramatically from 0.95 to 0.005. And now I'm getting kind of back to where I want it to be. So this percent time is gonna give you the time it takes to do this. So the wall time is 3 minutes actually. So it took me really 3 minutes and 39 seconds to run this. And I'm using NS here, the negative sampling loss function. Kind of the same, similar to the above one. But I could run multiple other iterations to see if I can get anything better. One thing I want to mention is that fastText is not mature yet, so be aware of the bugs and report them. But since this tool is very powerful in some of the applications, people are still using it regardless of the issues that might come with it. So to recap, we could see the power of transfer learning using pre-computed vectors in our example, our small example, but essentially the precision that we got from it is similar to what we had already without using the pre-trained vectors. This 83 0.83, 0.79 essentially is very close to what we got from that. And also the embedding approach results is very similar to bag of words results. In here we also had about 82%, 80% was 80%, I guess, 0.79% accuracy what we had at the end. 0.79 precision on train. So we could say this is a draw. But now let's imagine this is our first iteration. I want to show you a second iteration that I have here. That's the second iteration using the embedding. Everything is similar to before. The only thing is different is that in my normalize function, I am removing the punctuation marks from the text. Everything else is the same. You could see that similar input arguments result in similar metrics. And I'll do a model parameter tuning like grid search like before, but again the precision on train is 0.83, precision on test is 0.79 like before. So this is training on all data, not really that important for us right now. I am now trying transfer learning here using that Wikipedia and news text, all those. So see the description for this on the link I sent you. You could find it on fastText data. So I'm using this embedding, which has dimension 300. Make sure to set the dimension equal to the dimension of these word vectors. And I'm doing some iterations in here, and you see this is a good enough result I would say, but still I might actually this is a little bit better. So this transfer learning has now produced precision for train 87% and precision for test 83%. Still it's overfitting like the ones before we had using fastText data, and this is coming from the fact that fastText is a powerful model and our data is a small data set. But overall you see this could be a second iteration. I mean, in production I could replace this iteration with the previous one and claim that this is doing better. About 5%, I guess the other one was doing 82% precision for train data and 77% precision for test data. Now you could see one extra iteration, and this last step here from using the transfer learning, I didn't do a grid search on it because it's taking a few minutes at least to run each of these ones. In reality, you guys feel free to do it at work or in your research group. You can allocate time to do more parameter tuning and find the best. There might be better ones. Now we are gonna go and discuss a real scale problem using both of bag of words and embedding approach in the next part.